Okay, so we've gone through this chapter, we've talked about the concepts, how to calculate all these different values. I showed the pizza example in Excel, but let's just start fresh and do an example together to make sure that we really understand this. So we're going to use Excel. We're not going to calculate all these values by hand. You can do that with some of the other practice problems, but I just want to make sure that you're really comfortable with using Excel and the software to solve these problems. So a sociologist was hired by a large city hospital to investigate the relationship between the number of unauthorized days that employees are absent per year and the distance in miles between home and work for the employees. A sample of 10 employees was chosen and the following data were collected. So I have the data in Excel file. So in our Chapter 12, the Chapter 12 practice file, it's under the tab Absent. So you have the data there. I'm just working in a new sheet and a new tab just so that we can do this together. So what does it want us to do? Let's just do A through D. Let's develop a scatter diagram, and does the linear relationship appear reasonable? Explain. So let's do that first. So we can go to, insert recommended chart. So let's select our data. Whoops. And we want to go to, under charts, insert scatter. So let's select that. So I hope you saw I did that pretty quickly, right? Just go to insert, under charts, you'll see one with a bunch of dots. Just select that, and then scatter, just pick the one with the dots, and your scatter plot, your scatter diagram will come up. So we can just look at this. Let me zoom in just to make sure you can see this, right? And it looks like all these observations, like they're linearly related. We don't see some type of curve or anything like that. So a linear relationship is probably appropriate. We also see a downward trend. So that means as x increases, y is decreasing. So one thing we can do is, well, one, obviously if you were to hand this in, I want you to clean this up a bit, right? We have no labels for the x and y axis. You want to select the plus and hit axis titles and then label those appropriate. So one of these is days and one of those is distance, right? You'll want to do that. Something else you can do is just click on any one of the observations, and you'll notice little x's will appear on them, little crosshairs. Once they're highlighted, right click and select Add Trend Line. Add Trend Line, and a box will appear. And you have different trend line options. We want linear because the data are linearly related, or so they appear. And then if you scroll down, you can select Display Equation on Chart and Display R-squared value on chart. And those should appear. I'm just going to move them up here so that you can better see them. So this actually is giving us all of our regression information regarding writing the equation and the r-squared, right, the coefficient determination. So it's 0.71. So what does that mean in terms of interpretation? Well, it's pretty high. So this is indicating good fit with our line in our data. It means that 71% in the variability in our outcome variable can be attributed to the model that we have, so whatever our x value is. And then here's our equation. So Excel writes it a little bit different, but it doesn't really matter. So we have our intercept, right, is 8. So actually, if we look at this, right, this graph seems to make sense because the y-intercept is going to be somewhere around 8, right? You can see the line going towards 8, and then we see the slope, right, is m. It's the value that comes before x, right? And so it's negative. See how it's negative? So it's showing a downward trend, and it's about 0.34. So in terms of interpretation, what this is saying is that a 1 unit increase in x is associated with a change in y of negative 0.34. Units on average. So that would be the interpretation of it. So basically, as x is increasing, y is decreasing. So 1 unit increase in x, right, you'll see a change in negative 0.34 units of y on average. So that's the interpretation there. Okay, so yeah, what's the next? What else do we got to do here? Develop the least squared estimate regression equation. Well, we actually just did that. Is there a significant relationship? Whoops. Between the two variables, so we have to test this. So we want to actually do our regression. So let's do that now. Let's go up to Data, Data Analysis, Regression, select our variables. So y is the outcome. What is the outcome in this variable? distance. So we're looking at distance and how often people are absent. So I'm assuming that the distance is going to be our x variable. So the farther away you are is going to predict how many days you are absent. So our y is going to be days, and then our x is going to be distance. Right? I have labels and confidence intervals, output range. Where do you want to put that? I'm going to put that right here in D1. And then I'm going to plot our residuals. So let's hit OK. And the good news, oops, is that this is looking like what we found here. So let's bring our table over here, or our plot that we did. So we'll notice that the r squared, right, is 0.7109, right? Those are the same. Our y-intercept, right, is 8.09. That's our y-intercept, and then the distance is negative 0.3442, which is that. So, right, all this equation, right, all the information basically is converging. So this is good. This is making sense. So we already have this information in terms of, is it statistically significant or not? I think that's what it was asking us, right? Are the two variables, are they significantly related, right? So that's when we're going to want to look at our F statistic and our T statistic, right? So the F statistic, it's less than 0.05, so it's statistically significant. In terms of distance, right, the p-value is less than 0.05, right, they're the same. For a simple linear regression, these values are going to be the same, by the way. Again, it's less than 0.05, so we know that this is statistically significant. So we can say that distance, right, is associated with absenteeism, right, days taken off. I think that's what it is. Yep, unauthorized days that employees are absent. So yeah, so we have an answer to that question. Is there a significant relationship? Yes. Does the estimated regression equation provide a good fit? Explain. Yes, we already talked about that. Right, explain 71% of the variability in y. It's close to 1, right? It's closer to 1. It's 0.71, so it does a pretty good job. So that's more or less all that there is to it. The only thing that it could have asked is said, make a prediction. So we could just say, given the distance is, right, 15 miles, what would you predict for days? So we could do that. We could just plug in x right there for that equation, and we'd be able to get a predicted value of y. Two things I want to point out. One, say it said, predict the days being absent given you live 24 miles away. Well, notice that our data doesn't include anything as high as 24. So when you try to make predictions beyond your data, right, the data range that you have, that's called extrapolation, and that can be kind of dangerous because right now we really don't have data out that far, so we really don't know how the data behave, right, what things are like out there. So if you wanted to plug in 24 for x, technically you would still get a predicted value of y, but we really wouldn't be confident in anything about it because we don't have data on it. We don't know, maybe there's something that once you live 20 miles away, there's something different that causes the relationship between x and y to be different. So you got to be careful with extrapolation. Just try to use, x values for, within the range of data that you have. The second thing is you probably see me kind of ignoring the y-intercept in terms of is it significant or not. The y-intercept, really we typically don't interpret it, especially for a lot of the research that we do in management and business. That's not always the case, but sometimes actually it doesn't make sense, its interpretation of it, just because lines kind of just go on forever. And so sometimes actually the y-intercept sometimes doesn't really make sense. We don't use it other than just using it in terms of, making predictions for y. We don't really do too much interpretation with it. Really all that it's saying is that if the slope were 0, or if you had an x value of 0, basically what it's saying is what your y value would be. What would you be able to say about that, basically. So if we were to plug in x, for example, so for distance you live at 0, what would the outcome variable mean? Basically it would be 8. So basically it's saying that if you lived at the hospital, how many days would you expect to be absent on average? Well, 8. So it's just, you can plug it in, but sometimes it doesn't really make sense, but it's not too big of a deal. Again, we just use it more or less for plugging in to make predictions. We don't use it too much. Sometimes you can. Sometimes it does make more sense, but sometimes it doesn't. Honestly, in a lot of the research I do, we don't really interpret it much, and I think that's why it's just my own personal bias because of what I do and do not do with the intercept. I typically overlook it, but I just wanted to address that in case you were wondering, because it occurred to me that you're probably wondering why I don't talk about it as much, especially considering it's a parameter that we estimated. Okay, the last thing I just wanted to talk about was, it didn't ask about residuals or anything like that, but it's good, again, like I said, just to extract and plot those just to see if there's anything going on. These look kind of random, so I don't think there's too much going on. I think overall this is a pretty good fit for the data.